Alright, so we've been looking over acids and bases. I did have to check to see if this is correct. It's been a while since I looked at acids. I didn't cover it last year or the year before. But there are strong acids, weak acids, strong bases. You can keep your mask on. And weak bases. A strong acid is an acid that completely dissociates make sure I got that spelling right. In water, meaning 100% of it becomes ions. Weak acid is an acid that does not fully dissociate in water. So less than 100% of it will turn into ions. And the definitions are the exact same for strong bases and weak bases, except for it is a base, blah, 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 that completely disassociates, and a weak acid is a base that does not. And note, this is a very precise definition of 100%. It doesn't matter if it's an acid where 1% of it disassociates or 99% of it disassociates. It will still be considered a weak acid. So, for example, if we put in, let's see, let's find a good one. If I can find a percentage on it. So, for example, nitrous oxide. Let's say we have a 0.125 molar solution of nitrous acid. Nitrous acid is HNO2. And what we see is about 6.5% of the HNO2 molecules turn into H plus and NO2 ions. The rest of it stays together as HNO2. So, when doing titrations, the reason why I spent a lot of time yesterday looking all this up is I thought this might affect titrations. And Michael, keep your mask on. But it doesn't. As some of these H plus ions are being neutralized, it allows more of this to break apart. So whenever these are dissolved in water, it keeps the same concentration of H plus ions. It's always going to be 6.5% of it will turn into H plus ions. If you remove some of the H plus ions, it means more of this will break apart to keep it at 6.5%. I mention this because most people think the name strong acid means very powerful, and weak acid means relatively safe to handle. So, for example, vinegar. Vinegar is a weak acid. But that is not the definition of weak acid and strong acid. For example, hydrochloric acid. Or wait, I think it's not hydrochloric. Hydrochloric is a strong one. Which one is it? Hydrochloric acid. This is a weak acid. You take a single drop of it and get it on your finger. What this is going to do is it's going to pass through your skin very easily, and you're not going to feel anything. A few hours later, you're going to be in the most intense pain in your life as your bones begin to dissolve within you. And you could die from a single drop falling on you, I believe. It's a very, very powerful acid. If you get some concentrated hydrochloric acid, a few splashes on you, it would be dissolving your bones, making toxins. It could dissolve your whole hand after a few minutes if you dumped your hand into it. It's not, though, it's considered a weak acid. The reason why is because it doesn't break apart into H plus and F plus ions. Another thing, there are different definitions of acids. So, the first guy to work with acids, I believe, given credit or worth a lot, is Arrhenius. He originally thought that these acids have H plus ions in the water. We have learned that H plus does not exist by itself. That's just a single proton. It's hydrogen is a proton and electron, and H plus ion has the electron. These ions don't really exist in nature. Instead, anytime an H plus is next to a water molecule, it is going to immediately form H3O plus. It's going to immediately attach itself to a water molecule. And this is known as a hydronium ion. Oftentimes, we as chemists are lazy and we will write H plus. But you should know that anytime you see an H plus, it's really not there. It's H3O plus. So, again, this first guy didn't really know that. But his definition of an acid is something that increases the concentration of H plus, meaning H3O plus hydronium ions. So H plus ions are really H3O plus ions, hydronium ions. And since protons don't really float around in solution by themselves, hydronium is more technically correct. And thus, a base increases the concentration of hydroxide ions. So these will be called an aragonous acid or a aragonous base. We also have, and I'm not for sure on the pronunciation of this, Bronsted-Lowry acid. So the definition of an acid is something that donates a proton, and definition of a proton to another molecule. And a base is any species or anything that accepts a proton. From another molecule. We can see that this definition of an acid expands upon the previous one. This means we can get some acids that are some chemicals that may not have H plus or hydrogen in them, but still donates a proton to something else. Or we can have chemicals that may not have OH in them, but still receives a proton. And finally, we have the Lewis definition. It's the broadest definition. Oh, by the way, all aragonous acids are Bronsted-Lowry acids, because obviously if something donates an H plus ion, it's donating a proton, and anything that takes produces an OH would take a proton too. And this is, acids are electron pair acceptors. And bases are electron pair donors. So all aragonous and Bronsted-Lowry acids are all Lewis acids. So this is the broadest definition, most general. Includes a lot of things that would not be considered Bronsted-Lowry acid or aragonous acid. talking about sulfuric acid, the formula for sulfuric acid is H2SO4. When this dissociates, so this is a strong acid, meaning every single molecule of sulfuric acid will break apart into ions. This breaks apart into H plus and HSO4 negative. This right here is a weak acid. Yes, you can have acids that are not molecules. You can have ions that are still acidic, which means this won't constantly break apart. This will roughly sometimes produce H plus ions and SO4 to negative ions.
Wow.
Y'all cool it. Alright. So let's work on some problems we've been working on. Let's suppose that we took 250 milliliters of 0.125 strontium hydroxide solution. And we neutralized it with some 5 molar per bromic acid. What is the balanced equation? For this reaction. So what's the formula for strontium hydroxide? What's hydroxide? OH negative. So you know it's going to be some ratio of strontium to hydroxide. What will be the correct ratio? What's the... Where is strontium? Strontium is in group 2, so it's a +2 charge. So you need 2 OHs to counteract that charge. And what's the formula for per bromic acid? So it doesn't have hydro in front of it, so you know this is going to be an oxyacid. Oxyacid has no hydro in name. So we know bromine mixed with oxygen, O3, and it's a halogen, and this should be Br. BrO3 has a negative charge. All the halogen oxyions have -1. And this is... Ooh. So per tells us, so the ick tells us it's going to end. So this would be bromate. Ick tells us it's going to have an ATE ending. But the per tells us add 1 oxygen. So we're going to add an oxygen, make it BrO4, keeps the charge, and that's per bromite. So it's going to be HBrO4. So hydrogen with OH being double displacement will make water. And strontium with BrO4. And BrO4 has a negative charge while strontium has a 2, so we need 2 of these. Making strontium perbromate. So we need 2 bromate perbromate ions. So we have 4 hydrogen in total. We have 8, 9. So we need to double the amount of hydrogen. Let's see if that balances it. So 1, 2, that's 8 plus 2, that's 10 oxygen. That's 8 plus 2 oxygen. 2 bromine. 1 strontium, so this is balanced. So we know the ratio is 1 molecule of SrOH2 to 2 molecules of HBrO4. How many moles of strontium hydroxide do we have? So we're given that we're having 250 milliliters, which we can convert that into liters. We know 1,000 milliliters is in 1 liter, giving us 0.25 liters. And we're given the molarity of the solution, which is 0.125 moles per 1 liter. Liters cancel out, giving us moles. And we end up with 0.03125 moles. how many moles of per bromic do we need to neutralize it? Per bromic acid. So we know it's a 1 to 2 ratio. So we have this number of moles of this. We need twice as many moles of this, right? So we just double that number. We need 0.0625 moles. And finally, how many milliliters of 5 molar solution do we need to add? Well, we know we need to add 0.0625 moles. And we know the molarity is 5 moles per liter. And we know that there are 1,000 milliliters in 1 liter. So moles cancel out, liters cancel out, leaving us with milliliters. Thus, we only need to add 12.5 milliliters to 250 milliliters of 0.125 strontium hydroxide to completely neutralize the acid and base and make just water and salt. Make sense? So we have different ways of doing concentration. We have molarity. It's most useful for science. That's grams solute per liter solution, per 1 liter of solution. We have percent weight, or weight percent, expressed as W/W, which is mass of solute per volume, per mass of solution. We also have another weight percent. I don't like the fact they use the word weight. It should be mass, which is weight per volume, which is mass of solute per volume of solution. And this is usually how it's expressed if you're adding a solid to a liquid. This is usually what you'd see if the solute is a solid. And volume percent, which is volume per volume, which would be volume of solute per volume of solution, which is usually how they report volume added to, a liquid added to another liquid. So let's say you bought some ammonia. And you bought 2% ammonia. I believe often they use weight by weight measurement. And let's say the overall density, let's say you measure the density of the solution. So this is ammonia solution. Let's say you measure the density of it to be 0.957 grams per cubic centimeter. And cubic centimeter is the same thing as milliliters. So grams per milliliter. My question is, what is the molarity of this concentration? How strong is this ammonium solution if they tell you it's 2% weight by weight? Speak up. Oh, no, what's the molarity? Concentration. So remember, molarity is grams per liter, grams solute. So grams ammonia per 1 liter solution. Well, first we need to figure out how many grams of ammonia do we have. So if the solution, the total density, is 0.957 grams, so this 2% right here, this 2% means that there are X number of grams of ammonia per Y grams of ammonia solution, and when you divide it, it equals 0.02. We know the density of the final solution, so let's just make up and assume we have 100 milliliters of it. So let's pretend for a second we have 100 milliliters of it. Then we can figure out how much 100 millimeters mass would be. So we have 100 millimeter solution, then I take 0.957 grams per milliliter. 100 millimeters would have a total mass of 95.7 grams. So this is how much a 100 millimeter solution would be. And I know that 2% of it, 2% of the mass, is ammonia. So 2% of the mass is this. So to figure out how much the mass in a 100 millimeter solution would be, I just multiply this number by 2%. Grams times 2%, and 2% is 0.02. It would be 1.914 grams. So that means if you have a 100 millimeter solution, it would contain 1.914 grams of ammonia, and the solution would have a total mass of 95.7 grams. And that's how they got the percentage. 1.914 grams divided by 95.7 grams is equal to 0.2, which is 2%. To figure out molarity, we thus take grams, because molarity is grams per liter. Well, we know what a volume is. We just made up a volume, 100 milliliters, and we know how many grams is in it. So 1.914 grams per 100 milliliters. All we have to do is convert to liters. There's 1,000 milliliters per 1 liter. And that tells us that this is a 19.14 molar solution. So, yes. So even though it's only 2%, look at how high the molar is, how high the molarity is. So even though it says 2%, it has extremely high molarity. That seems odd to me, but I'm about to go check. Molarity of 2% ammonia. I'm assuming it's because NH3 is so. Did I make a mistake somewhere? Oh, yes, I did. This is wrong. I made a mistake. This is grams. Molarity is moles per liter. So I need to convert this into moles, grams into moles. So nitrogen has a molecular weight of 14, roughly, 14.00674. Hydrogen is roughly 1.007943. And ammonia is NH3. So the molar mass of it, and I'll just rewrite it. So we have 1.914 grams in 100 milliliters. We need to convert grams into moles and milliliters into liters. So there's 1,000 milliliters in 1 liter. And we know from calculating the molar mass, there are 17.03056 moles and grams. And I need to put that number on bottom. Grams per 1 mole. So that grams cancel out. Milliliters cancel out milliliters. And I'm left with moles per liter. There we go. This is a more realistic answer. 1.124 molarity. Because 2%, I saw 17, it didn't look right. So in summary, to calculate molarity, we're looking for moles per liter. And we're given that the mass or weight of ammonia divided by the mass of the solution is 2%. So you can just make up a random volume to start out with, because concentration doesn't depend on volume. If you have a single drop, it would be 2% weight by weight. Or it would be, or if you had a giant gallon of it, it would still be 2%. So it's always good to just make up a nice number. I always use 100 milliliters. 100 milliliters is a good starting point. Or you could just use 1 liter. 1 liter would make this calculation go away, because you don't have to convert milliliters into liters. And I think that's it.